Welcome to the Python Programming Tutorial Series for Climate Mathematics Theory and Applications, Chapter 10, Advanced Python Analysis and Plotting. In this video, we will review area-weighted averages and a spatial distribution of trends. Let's begin with Section 10.4, Area-Weighted Averages and Spatial Distributions of Trends. Starting off with EOF from detrended data, we are using the data that was used in the previous video, that GPCP ST data that can be downloaded from the link that is in the previous video. We're going to go ahead and redefine some variables, redefining our munj variable, our GCPC dat variable, our GPCPJ, which only includes columns from the munj variable, computing that climatology using the means for every column and the standard deviation, which will be our STJ. Next, we're going to go into creating the desired variables for our detrended data. We're going to go ahead and create an enum-j matrix. Using the highlighted line, we go into our GPCP dat. We locate all the rows, but only the munj columns. We transpose this matrix, subtract our climj matrix from that, and divide by our SDJ matrix. Finally, transposing it to get our final enum-j matrix. Next, we are computing a V-area matrix, which will be made from the cosine of the GPCP-ST, all rows, first column data, multiplying that by pi divided by 180, and this will be our V area. Our enum A is going to be created from that V area times the transposed version of our enum-j matrix. Finally, we do want to verify that we do have the right shape, and we in fact do get a 68 by 10,512 shape outputted from this enum A matrix. Now, time to actually compute the detrended data. We are going to name this detrended data GanSat, and it will be the enum A transposed matrix, where we are taking the sum along axis equal to 0 and dividing it by the sum of our V area. This will give us a 68 sized array that has our detrended data within it. Moving on to figure 10.12. We are going to set up our figure using that PLT figure function, create a time variable using the NP line space between 1948 and 2017 with 68 points in between. We're going to set up a linear regression object using the linear model package, accessing the linear regression function. We're going to name this linear regression object LM. We are fitting our LM to time by GanSat. We do need to reshape our time variable into a -1 by 1 shape to allow it to fit into our linear regression object. Then we are going to use our newly fitted LM object to predict what the data would be if we stuck in a time variable into our linear regression object. We're going to name these predicted y values pred. Next, we are going to go ahead and plot our time by our pred variable that we just created. This will be a dashed line in the color of red with a line width of 2. We also want to plot our actual data, which will be time by our GanSat. We are going to plot it on a dashed dotted line with the color of black. We're going to set our title, add some text to our plot, set our Y label, and set our X label. Wrapping this whole block with a PLT show, we do get the global average GenSat anomalies from the NCEPRA data. We can see that we do have a linear regression line going through our data, and it does fit it very well considering our y-axis. Our black line represents the GenSat data that we created in the block above. Moving on, we're going to go ahead and recreate the desired variables using the same methods that we used up above. We're going to redefine MunJ, GPCP DAT, and GPCPJ, as well as our ClimJ matrices. Redefining these just allows us to ensure that we have the right data inputted in each of these matrices. We're going to define a function that makes an instance of our function. This definition will be for the anomj underscore function 3. We're going to create a data frame of all zeros with columns dictated by TM1 on our MunJ index. Then we are going to use this data frame and we are going to add our values that can be found in the GPCP DAT location, all rows in the MunJ columns in each index I, and we are subtracting our ClimJ matrix from these values. We're going to return the result of this computation in this function. We're going to go ahead and use this function and name its result anomj. Next, we are creating our time variables. Time is going to be our line space between 1948 and 2017 with 69 points in between. We're going to create a trend V function and an instance of that trend V. Our trend V function can be seen highlighted on the screen. We're going to start with an array of all zeros, and then we are going to use our regression object fit on our time and our anomj matrix, and we are going to go ahead and grab each regression coefficient and input it into our trend V array and return that filled trend V array out. We're going to go ahead and create an instance of trend V and name it trend V. Next, we need to reshape our data into the desired form. We're going to name this map mat1, and it will be the reshaped version of 10 times our trend V, and we're going to reshape it into the shape of 73 rows by 144 columns. Next, we are going to go ahead and create another function and name it matv1 function, seen highlighted on the screen. This function will create a zeros matrix that is 73 by 144 in size. We're going to enter a nested for loop and go ahead and fill all of our values in our zeros matrix that we created at the beginning of this function. This matrix will either be filled with values of 1 or it will be filled with values found in our map mat1, which was created in the block above. We're going to go ahead and use this function and name the result mapv1. Once again, we are creating another function and creating an instance of this function. This time, our function will be named mapmat underscore function, creating that matrix of zeros and filling it with either a -1 or the value of map v1. which was created using the function above. We are going to go ahead and name this instance of this function mapmat3. Moving on to figure 10.3, we're going to prepare our figure using that PLT figure. We're going to use the base map package to put the cylindrical projection onto our map. This line that is highlighted on the screen creates a cylindrical projection map. We do need to shift our data because we are plotting on a longitude-latitude map. So we are going to use that base map instance with our shift data function on our long values using our mapmat3 data. We are also setting long 0 equal to 180, which will make 180 degrees the center of our map. We're going to add some coastlines, draw our parallels and our meridians, and also drawing our country boundaries on our map. We're going to set limits equal to the line space between -1.1 and 1.1 with 50 points in between. And now we are going to go ahead and plot our contour map. We're going to use that PLT contour F function on our longs 2 by our lat values using that data 3, which was created in our shift data function. We're going to use the contour limits dictated by that limits variable using the color map jet. We do want to print our color bar, which can be printed from the highlighted line. We're going to set our X label, our Y label, and our title of this plot. Wrapping that with a PLT show, we do get the trend of the NCP. We do get the trend of the NCEP RA1 January 1948 to 2018 anomaly temperatures. We do want you to notice how these temperatures that are being shown is degrees Celsius divided by 10. Moving on to section 10.5, GPCP precipitation data analysis and visualization by Python. We are going to go ahead and download the following data set and put it in your active folder. It can be found at the highlighted URL. Once you get that data set downloaded, we do want to import it into Python using the netcdf package, accessing the dataset function, and inputting your dataset name in read-only mode. We're also going to define the variables that can be found in that dataset. We're going to go ahead and grab the longitude, the latitude, the time units, and the precipitation data found in this dataset, naming them in a conventional naming method. Moving on to figure 10.14, we are going to plot a 90 degrees south by 90 degrees north temperature along the meridian line at 180 degrees east. Defining that NC_X variable from -90 to 90 with 72 points in between. We are using the PLT plot function on our NCX by our pre-CNC variable with index 0, all rows, 63 column with the color black. We're going to set our X label, our Y label, and our title, wrapping that block with a PLT show. We do get this precipitation on our meridian line at 160 degrees east for January 1979 plot. Moving on, we are going to help create some data frames so we can go ahead and observe some things that are happening in this precipitation data. We're going to write the data as a space-time matrix with a header. We're going to go ahead and set pre-CST equal to the matrix of zeros dictated by 10,368 rows by 451 columns. We're going to let temp equal to the pre-CNC of the 0th index, all rows, all columns. Now we are going to fill the pre-CST with the data from pre-CNC that was grabbed directly from the data we are using. We're going to go ahead and enter a for loop and set each column in this pre-CST matrix to each index that has been flattened into a single array from our pre-CNC data. Next, we are creating and reshaping our lat and long variables to prepare them to insert them into a data frame. Our lat is going to be a list of our lat vals times 144, which will repeat this list 144 times, and we're saving this as lat. Long 1 will be the repeated version of I by 72 times for I in our long vals.data, which was grabbed directly from the original data set. Then we are setting long equal to I for J in long 1 for I in J. This will just allow us to have 72 repeated long vals, the same size as our lat variable that was created above. Going into our data frame creation, we're going to start with our lat and long variables, blending them together into a GPCP ST underscore data frame. Then we are using this data frame and concatenating it to our data frame that is dictated by pre-CST along the axis 1, which is the columns axis. We could go ahead and print out part of our data frame if we wanted. We're going to go ahead and print out the 889 through 892 rows with 0 through the 5th column. And printing this out, we do get this data frame to pop out. We have rows 889, 890, and 891. We have our lat column, our long column, and then followed by all of our precipitation data columns. Moving on to make a unique color map and our desired color map, starting off with a colors array dictating however many colors you want. The order of these do matter. We're going to go ahead and reverse that array to make sure that it's in the right order that we want, and use the new colmap function on our colors array, and this result will be called my colmap. Moving on to figure 10.15a, we're going to prepare some variables for plotting, and then we are going to plot our variables. We are going to make our climmat equal to the 0th index, all rows, all columns of our pre-CNC data frame. We're going to enter a for loop that will add our climmat to every index in our pre-CNC array, and we are going to name this computed matrix equal to our new climmat. We are now going to divide our climmat by 451 and set this newly defined climmat equal to mapmat. We are going to ensure that our values are suppressed in the 0 to 10 range using the highlighted for loop. We're going to set up a myInt variable that is going to be the line space between 0 and 10 with 11 points in between. Go ahead and prepare that figure using a PLT figure. Going ahead and naming our base map instance trend, which will have longitude and latitude dictated in the highlighted text. And this base map will have a cylindrical projection. We do need to shift our data, naming our longs 2 and data 3 by our shifted data operating on our long vowels, and our data that we are going to also be shifting is dictated by matmap, with our middle longitude point being 180 degrees. We're going to add our coastlines, our parallels, our meridians, and our country lines to this map as well. Actually getting to the plot of our data, we're going to use that contour F function. On our longs2 variable, by our lat vowels, by our map mat, with myInt as the levels of contour levels, and my col map as the color map of choice. We're going to go ahead and print that color bar dictating specific tick marks on it, set our X label, set our Y label, and set our title. Wrapping that with a PLT show, we do get this figure out, which represents the GPCP 1979 to 2016 precipitation climatology, millimeters per day. Just to verify the shape of that map-mat matrix, we can run a shape function on it. We do get the shape of 72 by 144. Next, we are creating and preparing some more data for our B plot in figure 10.15. We are going to create an SD map that is made from the 0th index of the pre-CNC, subtracting that clim-mat matrice and squaring it. We are entering a for loop and setting our SD map equal to our original SD map, which was made in the beginning of this block. We are adding the same function that created the SD map, but we are adding it to our already created SD map for each index in range 1 to 451. Then we are going to redefine SD map as the square root of our newly defined SD map divided by 451, setting SD map equal to my map to prepare it for plotting. We are going to suppress all the values in this matrix between 0 and 5 using the following for loop. Moving on to figure 10.15 part B, we're going to set up a levels for our contour levels between 0 and 5 with 25 points in between. We're going to prepare our figure using that PLT figure function. Go ahead and set up a base map using the cylindrical projection, just as the plot above used. We do need to shift our data because we are on a plot. In very similar fashion, we are using long vowels. Our data in will be the map-mat data using that long _0 equal to 180. Drawing some coastlines, parallels, and meridians on this map. Now comes time to plot the actual data using that PLT contour F function. We're going to be using longs 2 by lat vowels and projecting our map mat onto our base map using the levels dictated by myInt with the color map dictated by my col map. set the labels and color bars in the same fashion that we used above, wrapping that whole thing with a PLT show. We do get the GPCP, standard deviation of precipitation millimeters per day plot to show. We do have all of our values suppressed in between 0 and 5, overlaid our map mat matrix. This concludes part 3 of chapter 10, Advanced Python Analysis and Plotting. Join us next time as we dive deep into chapter 11, Python Analysis of Incomplete Climate Data.